Yo, we're live by the way on YouTube, so like don't say anything. You don't want the internets to desktop. Oh, yes. Okay.
One's USB-A, the other's C, so which
Oh,
works.
sweet. Jacopo, if you haven't sent it yet, you can Okay, just put it on the flash drive and then I'll Oh, flip it around. Yeah, it's okay. Desktop. Yeah, we can probably make it big. Yeah, sweet. Okay, I think we're live and streaming. And then, yeah, this is your workshop. And then you just need a MATLAB.
Yeah,
Okay.
and I'll need to update the Git probably download it again that time. So I've updated that file path.
Okay. Yeah, I'll just pull it right now. Okay. All right. Yeah. And then you don't need, oh, yeah. Okay. I think you're good yet.
Are we good to go or should we wait a few more minutes?
Oh, yeah, yeah. Let's just wait a few more minutes.
Okay.
But you're streaming, it's live.
Thank you very much.
And yeah, I think we're ready.
Amazing.
All right, let me know if you
Thanks,
need anything.
partner.
Yeah, no problem.
Amazing. Thank you.
Okay. And then the microphone, so the computer is recording mic audio, but then you can use this.
Okay.
So you just switch this on, and then it will allow you to talk louder.
Great. Okay. So once we've switched this on, we don't need to
Yeah,
keep track of it anymore.
yeah, it'll go through all of it. So
Okay. Should
cool.
I carry it with me, you think, or
Yeah,
I'll probably
probably.
stay around
Yeah,
with it?
you can always just
Worst case, I'll
put it back. Yeah.
Okay.
Okay. Cool. The rest will be approved. Okay. Yeah. Thanks, man. Yeah. So that's solid.
So I think this should be very convenient. Very large Facebook. And it makes it so it's weird. I really kind of hate it. Often is what the face is that that's what they at last night. And that's what they say. Stop. What's running on? Sorry, it's sorry. He said, I understand. Okay, so what's going on? So I think the idea is part of this type of just to have not that is not what's this is instead of class relations. If you want to public all of them, and we're public instead of yeah. So what's happening? That's the see what you hear how you yeah, but that's not what's what mean is that this is correct now. So it's not this is correct shape of the baseball and what it looks like correct. And it also should be like things like that this it sounds like juice versus risky going. Because okay, my story is special is to not even like that wouldn't affect like responses. Like without having setting out it's setting with levels. Seconds, that's a good yeah, but what's I think it's strange that because this is properly gonna then it's you're not yeah. So in particular there are feature yeah, so yeah. It should start at either so I was surprised. You've gone from living for the audience. It's just yeah, yeah. Yeah, no, that's definitely a lot. That's like yes, yes. My control. The reason why I said it's like it doesn't want me. Maybe I'll get this. Okay, so there's a so let's look at nice to one. This needs to have. So it's like last Oh, no, jumps. Just it's I don't so. It's nice. Yeah. It's fine.
Can we make this like I think that's maybe like a little better. Okay, so what's the problem?
That this version is still the old one, whereas VS Code, you can see that you did pull the latest one,
Mm-hmm.
but MATLAB still sees the old path. So we either have to,
Oh, this is in the download. Oh, okay.
right,
Yeah, so do you want to just
just change the path and
yeah, so we can are your images in GitHub?
images are not in GitHub.
Okay.
They are in the folder that we can.
Should I just copy? I can just copy it. So I can just take this,
That's
right?
the easiest, yeah.
Okay. And then
Again, I
GitHub.
just didn't want to.
Oh yeah, yeah. Summoner robotics workshops, perception mapping challenge. Okay. I think if you paste that there, then so then if I close these, and then I think that's it.
Let's see, we can check just following at the bottom. There's an update here in the path. Yes, that's
Okay.
the one.
Okay.
Thanks, Parker. Cool. And I'll try. Expand. There we go. Yeah, I might try to magnify, but
Yeah, you could. We could probably.
yeah, I can reduce the bars of the and the size.
Yeah.
Okay. Thank you.
All right.
I'll wait 5 more minutes maybe and then start doing. Okay, we'll get going. Maybe I'll give a couple minutes just to download, get stuff, and I'll check if the one. Okay. Hello, everybody. Before we officially get started, I just wanted to check if anyone has had any issues downloading from the Git repo, any of the material, if everything was successful, including the images, the image set on the OneDrive on the URL that we linked. If you haven't done it so, I recommend, I think this is a good time to go to the repo, clone that folder, and download the image sets. This way you don't have to think about it for the whole workshop and you can enjoy the rest of it. But yeah, this is also a good time to speak out if you have any issues with that. Well, okay. Let's see. How many of you have already downloaded the MATLAB code and the image set successfully? Okay, not too many. Just to get an idea, are others planning to download? Because I think the fun part will be getting to the challenge. So you don't have to, of course. That's what do you mean by solver? There's some code on the Git repo. All you need to do is to clone the whole folder or download the whole folder as a zip file. You can open that in MATLAB and In addition to that, we'll need an image set separately. So the code I currently have on the screen should look like the one you've downloaded from the repo. Just to double check before getting started, are folks trying to download things right now or okay, perfect. So in the working, I'll give a couple more minutes so we can see if these issues will come up later anyway, so I'd rather solve them now. Which are the download ones? Only images, so that on the list of you can download it's just not funny, it's just things are that's just things you don't special that's just yeah there is yeah and then you just drag it over see that what's in there yeah it's a zip file and it's just not packet news for us there's other things to try over yeah that is oh yes definitely yeah character suggestion is yeah it's problems no, it's usually sad as it shows that those suffering. Here's your foods. Oh, I like what's the next? What are you asking? I don't know. Yeah. Yeah, you know, this is the first one, right? He's considered there. He's in here. Yeah, there's cookies around. Yeah, so they're being inside the really compare that the camera is so I need to see again that's all. Yeah, the truth is just yeah, that's where so much is right is average so it's very strong. It's down also. You can eat. She will be able to breathe. Yes, it's just what you need to sign off when you months that you just get it out. I know this. That's something that you just do that. Just the real to provide for service that's needed for yourself and what consider officers sufficient as no longer Just a quick clarification for everyone since we got these questions. We'll be running the mapping demo challenge, mapping underscore demo underscore challenge dot m file as the main script. And you need to have your images folder in the same, at the same level as that main script. Okay, otherwise it's not gonna find your images. If you still have issues, just raise your hand. Maybe we'll get started in a couple minutes. What's that? The images? I know, right? I tried to find good scenario with this responses and any of it. Yes, so I want to achieve that. I think now you have there is yes. Be careful with nested folders. There might be an image folder inside another image folder, which could be why MATLAB cannot find images. So if you have an image folder inside another image folder, you would need to move that up at one level. It works. Since you were such a good was yeah, I think Yeah. The navigation toolbox should also be installed with Parmesan and on that later in the so but it's a lightweight toolbox, so it shouldn't be long for itself. It's like looking on the scene. That's it. It's fun. I don't know. That's what makes it fun. You need that is for this is so we are it's that's when you see the conversations. But three, four, five. The five. Yours was practice was it was but when you know it's all random turn it kind of so it's like always open so so scary things so this is that right we better see how yes it needs to be or we try to get over take the right probably has that was gotta get this so weird. So they just if you're still trying to download from Git, it turns out you have to navigate all the way back to what's it called, Summit Robotics 2024, the root folder, and you have to zip the whole thing. Otherwise, it won't let you zip slash download the subfolder mapping workshop. I didn't know that. I just learned it. So if you're still struggling on how do I get this thing from Git to my laptop, that's how you need to navigate back and download the whole thing. Okay, let's see. How many of you are still trying to set things up? So oh wow. Okay. The what if I go around table by table and I think that's gonna start from the bottom there.
Is anyone? Sorry, guys. See, images of macOS. Whatever.
So the images should be downloaded from the OneDrive URL, not from GitHub or anywhere else. Otherwise, you won't be able to unpack them. Yeah, it's a good call.
Yeah, my religion is very slow.
It is slow. The way it's set up right now, it's performance is not optimal.
Yeah. Oh, okay.
So I think that's the color. So we have a blender and okay, so most of them well, I guess will be set up and running. How many people are still trying to set them down? Okay. Already on song, this is nice.
Yeah.
All right, let's get started or try to do so. I think, yeah, most of us are set up. I will completely understand if you get distracted here and there to resolve that last bug, but let's assume we're all 95% there. Three Sigma, right? So, welcome to the Perception and Mapping Workshop. Thank you for joining. I'm excited to go through this together. Oh, wow. Wait, typically this is done at the end. Some encouragement. Okay, great. So, what I'll be covering today is trying to provide, well, I'll introduce myself and try to make an argument of why I'm here, although I don't know if it's a good argument, but we'll see. And then talk a little bit about what I've been working on, which is at the intersection between aerospace and robotics. We'll provide a very brief overview of perception for robotics, but then in this specific workshop, we'll really zoom into robotics and perception and mapping applied to space problems, and specifically, as you might have seen in your plots in MATLAB on asteroid navigation problems. Okay. I would love for this to be an interactive talk. 1 hour of talk is long, and I'll probably try to keep it within 50 minutes. So please feel free to jump in and either raise your hand or just speak. All right. This is where we start today. So imagine that you are a robot, aka a spacecraft in this case, these flying robots in deep space. And you take a picture and you see something like this, right? And as an autonomous system, which a robot is, you need to answer some questions. There are many more, but some representative questions could be, where am I? What am I looking at? What is this thing that I'm looking at? And will I be crashing into it, onto its surface, or will I escape onto an escape trajectory? All of these questions, of course, are really important, especially considering the closed loop that you all are familiar with between perception and motion planning. And in aerospace, we have a different jargon. We call it guidance, navigation, and control. There are many similarities, though. So, in order to have the whole system to work, we need to tackle the perception and navigation part, which is what I'll be focusing on in this talk. So hopefully this first picture got you excited. By the way, this is asteroid Bennu, a tiny 500-meter asteroid that was explored by NASA's OSIRIS-REx mission. So just a quick introduction. I was told to make this slide. My name is Jacopo Villa. I'm from CU and specifically from the Laboratory for Atmospheric and Space Physics. I was previously a grad student at CU in aerospace engineering. So my background is mostly on aerospace engineering, but I'm very interested in research and technologies at the intersection between robotics and aerospace. Although even describing it this way, I would say it's becoming outdated. I see it more as technology evolves, there will be a more blurry line between multiple fields, including robotics and aerospace. So my work focuses on robotics techniques applied to aerospace problems, specifically at this very time on asteroid missions. So I think I need some justification here on why we want to explore asteroids in the first place, since this is the main focus of this talk. And there are many reasons, some of which you might have heard of before. So asteroids can be seen as time capsules and of frozen rocks in the solar system that contain a lot of pristine material that for scientists can describe the origin of our solar system. The material can help us understand how our solar system has evolved and has formed. And that's because there are no, tectonic plates or geological processes that are perturbing the surface, right? Atmosphere, volcanoes, oceans, and everything that we have on planets. So it's very interesting for science. It's interesting for planetary defense. I'm sure you've heard the joke before that dinosaurs didn't have a space program, and thankfully we do. There are some speculations, some theories out there that life may have originated from space and specifically from asteroids or comets. So we'd want to test those hypotheses by exploring these bodies. I think the two that are particularly interesting, they're all interesting, but two of them that are particularly interesting for me are resource utilization to expand humanity access to space. We need to think long term and how we can stop leveraging and exploiting Earth, right, for resources, and we can start exploiting celestial bodies such as asteroids and comets to for life support system, for fuel, and for many other purposes to expand our access to space. And finally, there's a big argument that has been put forward recently that asteroids are a very compelling test ground for autonomous techniques. There's a lot of robotics going on on Earth. Unfortunately, in space, everything is so dangerous. There are, dangerous gravity fields. There are many things that can go wrong, and so typically the industry is very conservative. However, small bodies are more forgiving in a sense because of their lower gravity field, and they allow for more flexibility in operations as well as testing autonomous systems. Asteroids are everywhere. I'm sure you might have seen some chart like this before, but we're literally surrounded by them, especially by near Earth asteroids or near Earth objects, and they can vary tremendously in size from meters to hundreds of kilometers. And every mission is unique in that the size of the asteroid defines its gravity field and therefore its operational complexity and the science that we can get out of it. So, in a good and in a bad way, every asteroid is unique. So, it's important to keep in mind these aspects when designing a robot exploring an asteroid. CU is going to the asteroid belt, so that is exciting. And the reason why I mentioned this is that I've currently been working on this mission, the Emirates mission to the asteroid belt. And as you can imagine, I work on perception and mapping techniques related to it. What we're trying to do is to apply some robotics techniques to the mission. But what's exciting, and the point of this slide, is that this is a collaboration between the UAE Space Agency and University of Colorado Boulder. Which is the UAE Space Agency knowledge partner. We're going to fly by 6 different targets in the main asteroid belt and rendezvous, which means getting very close to asteroid Justitia, the last target, which is particularly interesting and compelling for science because it's very red. We don't really know why it's so red, and I'm not a scientist. I wish I could comment more on that, but it's a very compelling target. It could be water rich. There are many reasons to go there. And it's interesting that this is as much as we know today for what Justitia looks like from ground observations using telescopes. We really just get a rough sense of what this object looks like, which means once we get there, our perception and mapping really needs to start to kick in, and we need to characterize this body fully. So the what I'm hoping to get out of this discussion and workshop today is to get an idea of how we can go from something like this to fully autonomous perception and mapping around an asteroid. What you're seeing on the right is the Explorer, as they call it, the spacecraft that will be used for the mission. Those big circles, as you can imagine, are solar panels. So let me start from what is perception. So we briefly motivated why we should explore asteroids, taking a quick step back. What is perception, though, right? I understand many of you might be interested in broader applicability of these techniques that go beyond asteroid. I would hope so. If we all do asteroid stuff, it's kind of boring, right? So let me give it an idea of how perception can be defined. I'll still use asteroids as an example. I'm heavily biased here. But so the idea of perception is to process sensor data, to crunch numbers, to estimate some quantities. That's my summary. I don't know if that this is the best way to think of perception, but it's one way to think of it. And I need to give a shout out here to Professor Holzinger in the aerospace department, who was the first one I saw this chart, which makes a lot of sense, and it's very good to summarize and capture what perception is, or in this case, I think we were talking about estimation, but it's the same idea. So there is a universe out there, what the philosopher Kant called the noumenon, right? It's just what is, right? The true physical entity that is out there. It turns out we cannot observe that, not directly at least. A surface rock or a surface shape or an asteroid are all examples of these physical quantities. And then there are phenomena, right, or a single phenomenon. This is what we can observe using sensors. And in this example here, we're observing light or photons that are bouncing on the surface of the asteroid. They're reflected back into the camera detector. That's what we're observing. Of course, there are other phenomena and other sensor types that we'll focus less on today that can be used for perception. I know this part is boring, but we'll get to the fun part soon. Now, a fun GIF, though, before we move on with space stuff. This is an example, I'm sure you've seen even this one many times before, but of what perception looks like in more terrestrial or aerial robotic applications, right? And some of you might be much more familiar than I am with these type of applications, but some of these are autonomous driving, unmanned aerial vehicles. Maybe now humanoid robots are becoming increasingly relevant for perception. They've always been. Sorry to the humanoid fans, but and robotic arms and for manipulation purposes and so on. Common sensors used in this case are monocular cameras as well as stereo cameras, LiDARs, and there are many others, but these are 3 that are ubiquitous and come up all the time. I'll move away from this slide before I become too cringe because, as you can see, I don't know enough about this part, but I can comment a bit more on this one. So perception in space is kind of similar. We're solving similar problems. It's just different applications. So I'm reporting here a few examples, but before moving to the pictures, essentially what we're doing is we're using sensors to determine the spacecraft trajectory or orbit, the spacecraft attitude, which stands for spacecraft rotation and rotational dynamics. And for many applications, especially for a perception and mapping workshop, we're interested in a map, which oftentimes at planetary bodies we call a shape model or an elevation model or a topography model. A lot of jargon again, but very similar concepts to what's typically referred to as a map. You can see a few applications here. We can use perception for autonomously landing on Mars. That's what NASA's JPL has done with the Lander Vision system, where surface landmarks and image prediction, image correlation has been used to know where the lander was at any given time during descent. It's been used for asteroid missions at the bottom left for OSIRIS-REx natural feature tracking. You can see a kind of a similar concept at a high level where you take an image, what's called here a cropped image, and then you render or you predict that same image. And by matching these two patterns, you can identify a line of sight measurement that's serving as a navigation measurement to infer where the spacecraft is located. Another application is a more SLAM generic application where, in this case, we're approaching the Hubble Space Telescope and we're simultaneously localizing and mapping the robot, right? That's what SLAM stands for, using visual features once again. This comes from a research paper. It's not been demonstrated, at least not with this image set. Okay. Cameras are awesome. That's another thing I want to convince you about today. Why are they awesome? Well, first of all, they're awesome relatively speaking, and for some applications, right? But they are very lightweight sensors, which is critical for space applications, for aerospace applications in general. Mass is a big concern for system engineering. So if we can minimize mass on the sensor side, that's great. They're generally low in power because they're passive sensors, right? So cameras are collecting photons coming from the external environment. They're not actively, for example, emitting photons, which is what a LiDAR, for example, would do. Indeed, a LiDAR is more power intensive than a camera. They're ubiquitous, so they're well understood. They've been used for a long time. One important thing is that cameras provide this very dense, very nice representation of reality. We're so used to it because we have them on our phones and our eyes are kind of analog cameras in a sense, but maybe that's not true. But the point is we're used to this type of pictures. But if you think about it, it's awesome that you can scan and sense the world with such a density without having gaps, which is what happens with, for example, a LiDAR. Sometimes you can see these sparse point clouds, right? Um, there's so much information that is encoded in images, so many patterns to extract. And yeah, moving to the more estimation theory part of it, there is a lot of observability on the camera plane direction, or a lot of resolution, at least. In that, when you take a picture, you can really distinguish each pixel from each other. But an image gives you no observability in the radial direction, right? When you take a picture, you have no idea if that space rock that's shown all the way here is gigantic but very far from the observer, or it's a tiny pebble that's very close to the observer, right? Both could be true. So that's a key limitation of cameras. And zooming in a bit more, I think it's worth spending a few words to describe what an image is. If you think about it, and you might know this already, an image is nothing more than a set of picture elements, right? That's what pixels stand for, where each pixel can be seen as a bucket collecting photons. It's in principle as simple as that. Every pixel is receiving a set of photons and the brightness of a pixel. So if we look at this example here, the brighter pixels contain more photons. That's why they're brighter. Whereas the darker pixels have received less photons. Less photons have reached that specific point on the grid. So you can see an example here of an asteroid scattering or reflecting more light in this direction. this pixel will get more photons, qualitatively speaking, and as we move toward the peripheral regions of the detector, we get less pixels, or sorry, less photons per pixel. We can also use this example here to show what a saturated pixel is, right? You might have heard of importance of camera exposure. If you overexpose an image, the pixel will look completely white or to its full kind of pixel count that it can accommodate. That means that there might have been more photons that the pixel could collect. And that's generally bad because we lose information, right? We're wasting photons that we're not keeping. This is what a camera detector, one example at least, looks like. It's really a grid. It's a 2D matrix of pixels. Okay, so finally, perception for asteroid missions. I wanted to provide an overview of what the main problems are and trying to be a bit more um, not technical, but at least more schematic here to sketch out the problem, right? Why is it different from other robotics problems? So when we navigate in the vicinity of an asteroid, effectively what we're doing is we're taking images of the surface and we're extracting measurements from these images to estimate simultaneously or asynchronously the asteroid rotation period these objects are spinning. Hopefully, they're spinning around the pole. Sometimes they're also tumbling, which makes everything much more complicated. We need to estimate the pole direction, right? They're spinning about a pole around an axis of rotation. We need to know how that axis is oriented in the sky, right? In what we in aerospace we call the inertial frame. Um, of course, the key is to estimate a spacecraft trajectory. Oftentimes, that's what all of this is about, spacecraft trajectory to not crash into the surface as well, or escape, as well as a shape model for scientists. But to do so, we also need to co-estimate the asteroid gravity field, which can be complex. We're talking about potato-like bodies, irregular bodies. They're not spherical, and therefore their gravity is also complex, which makes all of this more fun. And there are other effects, such as the radiation pressure that you get from the sun, the photons that are colliding the spacecraft, that it turns out that over a long time, these tiny collisions are actually moving the spacecraft and making it drift. I'll also note, because most folks here are from a robotics background where stereo cameras are quite common, that in space, stereo cameras are not that useful, at least for asteroid applications, because as you can imagine, the stereo baseline between the two, the two cameras is too small to really sense any depth. We don't get any depth observability from a stereo camera itself. Most of the time, sometimes we get close enough that we start to see something. So keep in mind this scheme, because everything we'll be doing next will refer to this scheme. Okay, I think this is a good time to pause just to see if there is any, it's late at night and maybe it's this was the most boring part, so maybe there's no questions. Okay.
So when you have a saturated pixel, you talk about pixels and buttons. So is it possible for there to be any capture crosstalk between pixels that they get transferred?
It's a great question. The answer is yes. And that's definitely something that does happen. So, following the bucket analogy, what typically happens is that a saturated pixel tends to feed into neighboring pixels. And the exact mechanism by which this happens depends on the technology that is used for the detector and other details. But yes, that's definitely possible. Not only is it possible, but it's something that needs to be accounted for precise applications such as optical navigation in stars and similar things, where the photon count, aka the pixel brightness, is really important. We really need to nail that pixel brightness, so we need to account for that effect. So that's a good point. One more limitation for cameras: we cannot expose arbitrarily long times, especially because if we start to overexpose, we also start to get motion blur, or there are various ways to define it, but I'm sure you know what I'm referring to. Okay, so I sketched out this problem This seems pretty simple maybe on the sketch here, but there are some perception challenges that are quite unique to asteroid missions or small celestial body missions. And I'd like to divide this into two buckets of challenges. Challenges when we're far, long range, and in proximity. So when we're far from these bodies, remember these are previously unexplored bodies. So we have no idea of their spin axis and everything we talked about. And unfortunately, the images that we take, imagine we're taking this image, this is actually a comet. That's why you're seeing this comma getting out of the surface. That's literally radiated from the surface, from the surface. That's a phenomenon observed for comets, as I'm sure you're aware of. And in this case, we don't really know if we take a sequence of images, we don't really know if that evolution depends on a rotational effect or maybe the spacecraft that is moving or both, and which is which, right? How can we disambiguate the two? That turns out to be pretty challenging, especially when the shape is unknown a priori. We cannot use predicted images to correlate with the shape. So this is the just to give a sense of what the challenges are when we're far. We're looking at something that is rotating in front of us. It's very pixelated, very low resolution. We don't know how to solve all these parameters, size, shape, rotation, and the distance of the camera at the same time. When we're close, which is what we'll be focusing on, especially for today's challenge, there's another challenge that I like to illustrate with this couple of images. So you're still looking at asteroid Bennu, the one we've seen before. And what if I told you that you're looking at the same surface region, but as a human, let me ask you, would you be able to pick up the same surface patterns in these two images? How would you be able to find something to navigate with respect to, right? Can you say, oh yeah, I see a rock that maybe I can use to navigate? Maybe some of you might have seen this big boulder at the bottom, which is indeed part of both. Okay, that's kind of giving us one line of sight constraint, but it's also a very large constraint that is not a pinpoint reference, right? So you can see the point is it's not that simple for a human and for a machine, it turns out, to find reference points on the surface of asteroids. And this is particularly different from other vision-based perception problems for, say, mobile robotics. If we were to have a robot walk around in this room, it would be much easier to take pictures and find features or key points from frame to frame, right? Because the lighting in the room is pretty much constant. We have artificial light. The room is not spinning around the sun with respect to the sun. So you see how this is kind of unique of asteroid in terms of a challenge. Well, I'll show you some reference points, which took me a while to find. I spent some time to just manually find these points to bring the point across, but you can see that these images are affected by severe lighting condition changes, severe viewpoint changes, right? When you're looking at a boulder or a big rock, its appearance really changes significantly from view to the point that it's hard to find the same patterns. And features are kind of self-similar for these bodies, right? We have a bunch of rocks. How do we know which rock is which? Sometimes it's possible, sometimes it's not. And then in general, these bodies, it turns out they reflect light in an odd way. So how do we identify the same surface measurements across multiple images? That's the key challenge here. Here's an example of an animation simply showing some lighting condition in practice. This is a simulated, procedurally generated body. Don't bother about the feature tracking here. We'll talk about this later, but just wanted to show some of these effects and how surface shadowing is significantly changing over time, and how the appearance of these boulders is significantly changing, right, as we see these boulders from multiple perspectives. There are also benefits or easy parts for spacecraft navigation that we can't benefit from generally for terrestrial or aerial robotics. Specifically, we have very nice pictures of stars and the star field. And it turns out stars are spread across the sky, as you can imagine, with very well-known patterns. People have been looking at stars for a very long time. We know very well how bright they are. And so it turns out that given a picture, I'm taking here a cropped and magnified or in kind of a higher brightness version of this cropped version here, of the same picture I showed earlier, it turns out we can very quickly, with algorithms that are established, identify this pattern and find our orientation of the camera with respect to the sky plane, with respect to the so-called inertial plane. And this is something that might come as new information for robotics folks because it's not quite standard for other applications. But thankfully, we can make this assumption in many space applications where you will often see in papers. We assume that the attitude is known. And typically, that's one of those assumptions that people don't immediately, throw out the window. It's like a fair assumption usually because of stars. So that's one good part. And talking about the nerdy details for a second, that means that many estimation problems go from 6 degree of freedom, where we need to estimate the camera position and orientation, to a 3 degree of freedom problem because we already know the camera orientation. We only need to estimate the position. Unfortunately, that's not always true, as we'll see when we get closer to the surface. We don't really see stars anymore. Even if there are stars in the background, sometimes the surface is so bright that if we wanted to capture stars, we'd get overexposed images. There are ways to mitigate that issue that we can talk about if you're interested. All right, so I mentioned I've currently been working on this mission to the asteroid belt on EMA. And so we had to look at these challenges, right, and say, okay, how do we tackle these in this specific mission? And there have been various things in the past to tackle the same problems. I don't have slides on that. That's probably out of scope. But the point is, in the past, the process has been solved very manually. So to describe it in a very hand wavy way here, what was done in the past is that these landmarks, these surface landmarks, were manually tracked. Of course, there was still some automation, but there were human operators that would track these landmarks across multiple images, and that would bootstrap the process. In this case, that requires a significant software development effort, expertise, and lengthy timelines for proximity operations to characterize this body in its entirety. So we decided to leverage robotics and the emerging robotics techniques to solve this problem, which I think is quite exciting because, to my knowledge, is one of the first times it's been proven for this type of asteroid missions, at least to this extent and magnitude. And so this is what we came up with, what we call a waterfall perception pipeline or waterfall pipeline approach. The idea is pretty simple, is as we've talked about, there are many problems to solve. We need to solve the spin rate, we need to solve the pole orientation, and then the shape, and then the localization of the camera. What's nice is that we can not solve all of them at once. We can actually isolate the problems, as we'll see in a second, so that we start from one estimate, and then each estimate feeds into the next. So we start from estimating the rotation period, which will feed into estimating the pole, which will feed into estimating the shape, and so on and so forth. And so that's the proposed approach to decouple these problems. Maybe some SLAM enthusiast will yell at me right now, which I would understand, saying this is suboptimal. You need to co-estimate everything together. That's much more optimal. Just make a big graph, and which it's a good point, and yeah, it could be an alternative approach. It's this is just one of the potential approaches. Okay, so I have one slide for each of these, but then we'll really spend most of our time, especially with the challenge on the last part, which is more applicable to a variety of robotics applications, so shape reconstruction and terrain or surface relative navigation. So to estimate a period, I'm really just showing working principles here. We use something that's called the light curve. And I realized for some of these slides, it would be much better to have animations. Sorry, I didn't make animations, but please use your imagination to animate this image and imagine that this comet is now spinning, okay? What we're doing is we're tracking this comet as it rotates, and for every frame, we integrate the total brightness in the image, so the total count of pixel intensities in the image. And that's what we call the light curve. So you can see it's really a double summation for all the pixel brightness. And that's for a single, this double summation is really for a single instant, right? What we want to do is to track this light curve over time. Why? Because it turns out that if you track the light curve over time, you can see some periodicity in an object that is rotating. I'll borrow Parker's mouse here if he doesn't mind. You can see that if you look at this mouse, it changes. The brightness of the mouse is maximum here, is minimum here, and then it goes back to being maximum and minimum and maximum, right? So you can see how the light curve is actually encoding this periodicity. It's not going to be a perfect sign because shapes are not perfect, ellipsoids or something like that, but they're more irregular. This is why you see this odd shape here, and we need to use, Fourier fit to essentially find to extract that light curve. But that's the idea. And once you use a Fourier transform to bring this stuff from the time domain to the frequency domain, it turns out that oftentimes you have a very sharp peak corresponding to, depending on the body, either 1 or 2 times the rotation period. And that's how you can disambiguate very clearly what the rotation period of an irregular object in space looks like. Now, what's mind-blowing to me is that people do this, they've been doing this for decades, so we didn't come up with this technique, of course, but they've been doing this with telescope observations with subpixel objects, where every photon that you get counts to extract this light curve. And to give you an idea, the uncertainties on the rotation rate of the asteroid Justitia that will be approaching with the EMA mission is currently 30 milliseconds. That's how good we can estimate how an asteroid is rotating on the other side of the solar system in the main belt with this type of techniques, 30 milliseconds. So it's kind of interesting. But we'll want to do this again during approach just to verify that that's actually a good estimate. Okay. Any questions on, I know this is the furthest, we'll get closer and closer to robotics application moving forward. So yeah, of course. Exactly. If you had a perfect sphere, you would at best get some noise due to pixelization. If you have an ellipsoid, though, you can get a very good signal. So depends on what you mean by irregular. It needs to have some irregularity, at least around some axes, such that it would show this periodic component in its light curve. Yeah, unfortunately. Yeah, thankfully, as far as we know, virtually all the small celestial bodies we've visited so far are irregular. So that's an underlying assumption to all the work. If we find a tesseract or a pyramid, it would be interesting. That's an irregular that I don't know we want to find. Okay, so pole estimation. That's the next step in the pipeline that's fed by, or we estimate a rotation period first that informs the pole estimation part. Even in this case, I'm not going to spend too much time, but I think one interesting aspect here to emphasize is that imagine now we're getting closer to the asteroid, right? I should go back real quick here. We started the period estimation even at less than 1 pixel, and now we're getting into this territory where the object span is 100 to 200 pixels, which if you've seen this type of images before, it's kind of pixelated, it doesn't look great. But the other issue is that now we start to see the surface. And potentially, when the sun comes from the side in the picture, what we refer to as a high sun phase angle, doesn't matter the term, there can be a lot of shadowing. There can be a lot of shadowing effects on the surface, which can corrupt the signal. And for this type of applications, where millions or thousands of kilometers away from the object, these type of errors can really screw up the navigation solution. So the question is, how can we reliably use this type of images for navigation? And what's typically done is to extract the component in the image that is directly facing toward the sun, what we call the light robust limb. That component cannot be occluded by any other body, right? Unless there's a spaceship flying in front of it and we would maybe miss one photon. Otherwise, there is nothing in between the sun and that part on the left-hand side. So we end up using only those pixels, even though we take this picture and there is a lot of content. Unfortunately, we have to throw most of it away, at least for these applications, to make sure that we that all the pixels we use are good information. We'd rather use less information, but good information, rather than more information, bad information. So pole estimation, using these light, robust limbs, so we're really just keeping track of the contour of the object facing toward the sun. Imagine now that we are given two images. Oh, I'm sorry. Yeah, question. Thank you. Yeah, the limb is what I'm showing here as this highlighted set of pixels. It's in general, the limb is defined as the edge or the contour or the boundary between the foreground and the background. For space images, it's very simple, computer vision wise, to extract the limb because of the sharp contrast with the background, which is typically very dark, right? But in this specific case, when we say the limb, we refer to the light robust limb. So the subset of pixels that are both on the edge, right? So we use something that looks like an edge detection, is an aerospace version of edge detection, but on the edge, and then we only keep those facing toward the sun. So using these light robust limbs, if you imagine we have two images, which let's say are this one and this one, you will see this is a repeated version of this image, but let's ignore this one for a second. This was a good place for an animation. If we were to, well, let me take a step back. Remember that we've estimated the rotation period of the object, right? With very good accuracy, 30 milliseconds or something. So you can imagine that if this is my asteroid, the relative motion relative to the surface now fully depends when we're very far away, virtually to first approximation and maybe second order too, really just depends on the rotation of the asteroid with respect to the camera. Because we're so far that our motion looks rectilinear and we're moving somewhat slowly compared to the asteroid rotation. So if we take an image here and we take another image here, the motion between them will be dictated, will be driven by the rotational motion of the asteroid. That's the key concept here, right? Using that concept, it means that we can make a good prediction of the displacement or the relative pose between the two cameras because we're using the rotation period to predict this pose, which we know really well. However, the missing piece of information here is the pole. If we use the rotation period to rotate around the true pole, we get one solution. If we rotate around the bad pole, we get another solution. How do we know which is which? Well, it turns out that by casting our limb, by ray casting our limb out into outer space or into the scene, so it's a 2D to 3D projection, we can find intersections, and the points that are intersecting with the 3D surface, the more intersections we get, the more likely it is that that's the true pole hypothesis. Now you might say, but we don't know the shape and the 3D object in the first place. We don't know it yet, right? It turns out, this might be too detailed for this slide, but for those of you who have heard this term, is we can solve this problem using epipolar geometry or projective geometry. It means that we don't even need the 3D shape. I'm showing it here and to illustrate the concept, but it's important to emphasize that we don't need the 3D object shape. We can simply look at the intersection between these rays in projective space. So what this will look like is we take this ray, we project it onto the second image, and this ray will intersect with our limb, not the 3D object, but the projection of the 3D object, which is the limb in the second image, and vice versa. So higher level, the better the pole hypothesis, the more intersections. The worse the pole hypothesis, the more missed rays there are, like in the example at the top. The worse, yeah. The worse the pole hypothesis, the less intersection. It seems like a pretty simple principle, but based on this, if we look at this example, here we're using only 3 images from 0, 45, and 90-degree longitude. This is completely arbitrary, just to convey that we're taking a picture here, then the object is rotating by 45 degrees. We take another picture here after 90 degrees, right? And you can see that we can really only observe a thin slice of the surface, right? Even then, using only 3 images, we can nail the pole estimate, the pole direction in space up to 1 degree of error in this case. And we could get much better than this if we process more images. So this is how powerful images can be, and these principles of epipolar geometry, ray intersection, ray projection, to resolve physical quantities. So I would imagine much of this is not terribly relevant for your current applications and possibly future applications, but what I'm hoping to convey here is that out of images, we can extract a lot of information for the environment, and sometimes using information specifically by being informed by what we know, like in this case, by knowing the rotation rate, we can solve for something else, right? Which we couldn't solve for if we were merely processing image data without any a prioris. All right, so we're getting in the second half of it. Yeah, just wanted to briefly mention that there are other techniques to estimate the pole. One of them is to stack multiple images together. It turns out that if you stack multiple images or multiple silhouettes, so multiple binary masks to be more specific, this image that results from silhouette stacking encodes some level of symmetry, which then if you apply a 2D Fourier transform, you can really start to see this effect. The symmetry shows up in the amplitude spectrum in this case. And by running a simple symmetry detection algorithm, by sweeping through all the directions, the algorithm can accurately determine usually the direction of rotation for the pole. So there are other techniques. In this case, it's a bit less informed by priors, and it uses different principles. Yeah.
Is that something like PCA?
Not in this case. There are other approaches that I'm not showing here that are based on PCA or are related to PCA. PCA stands for Principal Component Analysis. It is very related though, and there are other techniques that can use PCA. I'm happy to chat more. Okay, so once we have a period estimate and a pole estimate, now we get to the fun part. We can finally resolve our object in 3D. And this first technique that we'll go through is something that some of you might have encountered before because it's more common in computer graphics, computer vision. It's called shape from silhouette. And the idea is pretty simple. By taking pictures of a 3D object from multiple views, and by then extracting the silhouette, which is the foreground, as you know, we were commenting before about what the limb is. A silhouette is a very related concept. The limb represents more like the contour. The silhouette is the full binary mask, but they're extremely related. So by using the silhouette and by merging multiple silhouettes, you can see the example of the hand at the top here. We can constrain spatially where the object is located, right? This is not providing an entirely accurate estimate of the shape, but it's more an occupancy constraint. We know the bounding volume wherein the object has to be located. Turns out this occupancy volume, because depends on images, is called the visual hull. It's the hull that we obtain for a given set of camera viewpoints. And you can see at the bottom here how the visual hull depends on how many pictures we're taking, right? As you would expect, the more images you take, you can see the example on the right, the better the visual hull becomes, the closer it becomes to the true shape. But it also depends on the specific viewpoints that you're selecting. If you're wisely selecting the set of views, you can get a better visual hull than the one you would get with the same set of views. Now, an important point here is that some places are fundamentally unobservable, though. So if we were to see this concavity here, no matter how many views you would use, we could not see that concavity. That's one fundamental limitation of visual hulls, that concavities in 3D cannot be observed, as well as in 2D, but some concavities can be resolved depending on the perspective. For example, if we were to look at this same shape from the top, we would now be able to see that concavity, that hole there, right? So a quick example of a shape from silhouette simulation for asteroids. Remember, in this case, we know the rotation period, we know the pole direction, so we can constrain all the camera views, and that's why we can That's how we can infer the shape, because now we know relative to the surface where the cameras are located by knowing the rotation rate and by knowing the pole. I can elaborate more on that, but you'll have to trust me that if you know these two parameters, it turns out that you can estimate pretty accurately where the camera is located. Yeah, you can see how in this case with this bilobed body, which is the same comet we were looking at earlier, we can resolve the shape as more images are processed from the top left to the bottom right. We're processing more and more images. Here's one more example of asteroid Eros. In this case, it's a different one. And there are two things I'll quickly emphasize here. One is that, as we just discussed, we cannot observe concavities, which hence the large errors in these two places. Asteroid Eros has pretty large concavities here that are simply not present in the visual hull. But also, these images are taken from millions of kilometers away, and we can resolve the surface up to 2 to 4% of the size of the asteroid, which is pretty impressive. So these techniques are powerful. It goes back to how sensitive cameras are to in pixel space, right? You can really, when we project a pixel into 3D space, that can really constrain our observations and our estimates. Okay, really quickly, limb-based navigation. Once we have a 3D shape, a visual hull, we can use the limb. We go back now to the concept of the notion of limb to navigate. Specifically, the way we can do that is starting from the left here. We now have a rotation period estimate, a pole estimate, and a shape model, a coarse shape from silhouette. We can use this three. Turns out the sun position in the solar system is very well known, so that's always given for free. So using these together with the sun, we can make a prediction of at any given time of what the limb would look like. Okay, so what you see at the bottom there is the predicted limb based on our internal models. By then matching the prediction with the extracted limb that we can extract with some edge detection stuff from the image, we can finally converge to the best solution for our camera hypothesis. Right? So we're making multiple predictions across a set of camera latitude and longitudes. These are multiple hypotheses. And there will be a hypothesis that's minimizing some residuals or some error metrics or some cost function. That's how we can infer the camera position, even if we have a core shape model using images. That's done by registering the limb with the observations. All right, I only have one slide to show that we can also use surface shadows to detect surface hazards for hazard detection purposes. And the reason why shadows are particularly powerful for airless bodies is that shadows are very sharp, right? They are sharp signaling on the surface of airless bodies. And we can use the same principle to detect landmarks, as you can see on the left side. So these two combined could provide more situational awareness if we're interested in detecting surface hazards, for example, for landing purposes. I want to get to this last part, and this will take me 10 more minutes, and then we can finally jump into the challenge. So let me go back real quick to this slide, which we showed earlier. I wanted to remind you of the main challenge we have when navigating in proximity of this asteroid, right? In proximity, it's very hard to find measurement associations. So the method we proposed for this mission, and now I suggest you pay attention because this is what you will be working on for the challenge, is a point cloud based, that's weird, a point cloud based navigation approach using visual point clouds. So some of you might have heard of point clouds before, and they're often used in the context of LiDARs or stereo cameras. In this case, we're using monocular cameras to extract visual point clouds. And at a high level, the process goes as follows. We take a picture, we detect some temporary surface features, right? Just key points that using feature detection algorithms. Now, here's the key. We only track these features using feature tracking over a short baseline, over a short stereo baseline, because remember, the key challenge here comes from lighting conditions. And the more time we wait, the more the surface lighting will change and the more the viewpoint will change. So we're trying to find a trade-off here between, okay, we need some stereo baseline to navigate. We'll go into the details, but we don't want a too large of a stereo baseline such that surface lighting is significantly changing from frame to frame, right? Again, for other robotics applications, it's fine to wait for a long time because the scene is not changing much. In Asteroid, it is changing much more. So we track features over a small stereo baseline. Using these feature tracks, we can use something similar to structure from motion, if some of you have heard of this term, to reconstruct a 3D surface point cloud, which can then be registered with the reference shape model that we already have, or with the previous point cloud, which is what you all will be doing in a second, with the previous point cloud to reconstruct a shape model, right? So that's how the process goes, and ultimately we can get a camera pose estimate. We get a camera pose estimate because by registering the point cloud with the reference, we can directly infer where the camera is located relative to that reference, right? When we move the point cloud around, because this point cloud is expressed in the camera frame, this point cloud is in the camera frame, we're also moving the camera frame itself. We'll see that we'll see that in this slide. So before and after registration, that's the idea. What I was just describing is that we firstly estimate the point cloud using triangulation relative to two camera views, right? We need at least two camera views to estimate the depth of these points. But now in the first step on the left side, we only really know where these points are located relative to the cameras. We have no idea where we are in space. So using point cloud registration, we can now stitch these points onto the surface, the reference surface or the reference point cloud, which helps us understand where we're located. Hopefully that principle makes sense. But of course, we can chat more even during the challenge in a few minutes. How long are we going long here? Okay, we'll wrap this up in 6. Okay, we'll wrap up the slide part in 6 minutes at most. So feature matching is the first step in this process, and just want to spend a few words to define what a feature is. It's a salient pattern in images that, because it's salient and because can be described, can be recognized in multiple frames, right? So we can use feature detection algorithm to localize these patterns. You can see an example here. We can then use descriptors or feature extraction process, as it's called, to essentially compute a feature vector, typically a 1D array that's encoding the information related to that specific feature. And then by matching these descriptors, these feature vectors, we can find associations between two images, which is what you're seeing here at the bottom right. That's how we can register multiple images. Keep in mind there's two registration parts in this process, right? Feature registration and point cloud registration. We're still in image space here, so it's still a feature matching registration. There are some examples that you can look into if you're interested. SIFT and SURF and KAZE, and if we talk about tracking instead of matching, there are KLT, Kanade, Lucas Tomasi, many different examples that you're welcome to look into more. These are state-of-the-art techniques. Once we get these feature matches, we can perform triangulation, meaning once we've matched features from multiple camera views, we can estimate the location of the 3D point. And the one thing I wanted to emphasize here is that ideally for triangulation, you can imagine that the larger the stereo baseline, or the distance between the two eyes, if you will, the smaller the depth errors will be, right? The triangulation errors will be. But there is a trade-off, as we talked about a few times now, that if we increase the baseline too much, the lighting conditions will also change significantly. So we want to strike a balance here where we have a large enough baseline to resolve the 3D points, not too large that lighting and shadowing is going crazy and we can't match those features anymore. Last step is point cloud registration. And currently we're using a pretty standard algorithm that, again, you might have heard of before. It's called the iterative closest point. I love it because it's so simple, but also oftentimes very effective, and it has its own limitations, which we can talk about. But the idea is that given 2 point clouds, a moving or source point cloud and a fixed or target point cloud, the algorithm goes as follows. It's really it can really be summarized in 4 steps. You firstly compute the nearest neighbor distance, as it's illustrated at the bottom here, between neighboring points, between closest points. That's why it's called iterative closest point. You will go then to estimate the translation and rotation and sometimes the scale factor between these 2 point clouds based on these variables, right? So this is the information that you use to compute the translational and rotational offset. You then go applying that transformation so that, for example, let's say these arrows are telling you, okay, we need a net translation toward the top. You take this point cloud, you move it at the top. Now they will be closer to each other, as you can see in the GIF example there. And you iterate this process. You can imagine that as you iterate, the point associations will get better and better because the 2 point clouds are overlapping more and more with each other. So that's how it goes. And ICP turns out to be very effective for many people. It's been criticized and it has its own limitations, but it really depends on the application. And for our purposes, we found it to be pretty good. So here's the example we saw in the previous slide. Last couple of slides, and this is kind of a segue to our challenge, is that we can use the same principle, stitching multiple point clouds together to reconstruct a map, or as we call it, a shape model of the asteroid. It's the exact same principle, but instead of stitching the point cloud to a reference shape to infer the, if you want, the world pose of the camera, we're now performing odometry, right? You might have heard of this before, to perform frame to frame displacement. And as a byproduct, we can also build a map. That's one of the principles behind SLAM, which we didn't go too much into details in this presentation, but the idea is that you can simultaneously build a map and localize the camera, right? Now, I have a caveat here, which we'll talk about in the next slide, is that this map looks good to a human eye, but it turns out that mapping is subject to drift. And oh, I've got one more slide before moving to drift. I'm just showing an example of what this point cloud based approach would look like when using real images, right? So this is not the simulated data, it's real images from the OSIRIS-REx mission, and it turns out that it performs adequately for practical applications. And I was talking about drift in that whenever we register consecutive point clouds, one unavoidable issue is that the camera poses will drift over time. Some of you might see the analogy with, let's say, integrating an IMU drift or something like that, right? Just in general, whenever you integrate some white noise or random noise, it will tend to drift over time. It's exactly the same principle here in that between every consecutive registration, we'll get some, hopefully zero mean, somewhat random noise. Unfortunately, this noise will build up over time and will lead to the drift. This means that if you don't correct for this drift, you'll end up with a biased or skewed map, which this bias can become pretty severe in some scenarios, some more than others. This slide also provides a scheme to introduce the idea of pose graph. If you haven't heard of this before, which is essentially a way to use graph theory, where we have nodes and edges, to describe the relationship, the geometric relationship between camera poses, right? Where each node in the graph is represented by a camera pose, and the edge, the connection, encodes the transformation between those poses. It turns out that this is a very powerful way to solve perception and mapping problems. In fact, there might have been a different talk today that would have been entirely on this. This is a very key concept in robotics, perception and mapping. Here we're looking at it at a high level, but keep this in mind if you're interested in this topic, and we can talk about this more. But you can imagine that by finding this mathematical framework to formulate the relationship between camera poses, we can then solve all kinds of optimization and fun problems. Here's an example of what loop closure looks like. Maybe we can look at the GIF on the right side first. You'll see that as this robot now finds that it's been in that place before, you saw what happened. It stitched the map back together because it recognized that there was a so-called loop closure. So by recognizing the loop closure, we can stitch back the map and significantly improve shape reconstruction or mapping performance. The example on the left is basically showing the same concept just in a static format, but on the left-hand side is before loop closure. Once we detect and close the loop, you can really think of it as a ring or as a as a rubber band, right? That you go back and link together. Okay, this is my last slide, and finally, the intro to our challenge to see if we've learned or got something out of this rambling. And so, of course, the topic here is asteroids. So your challenge, as you might have seen already, is also on asteroids. You have an autonomous spacecraft that is orbiting around asteroid Eros. It's a 20, 30-ish kilometer asteroid. Your orbit is around 50 to 60 kilometers in altitude. You're given an image set, the one that was hard to unzip, that you can use now to reconstruct the shape, the surface shape. And one of the things that are interesting about this challenge is that you're only given a handful of parameters. So in this case, we assume that the camera orientation is known. We said we can estimate that with star fields. In practice, we can estimate it through other things that we didn't cover in this talk. So we're given camera poses, we're given a stereo baseline, and the baseline is the relative position between consecutive cameras, right? So the key here is that in practice in space, we know this relative position fairly well because we have pretty good orbital dynamics. So propagating the dynamics is quite standard, and we have small errors when doing so. But these errors drift over time, right? So we only know the baseline, we don't know the full trajectory. Baseline, small errors, full trajectory, large errors. So you're given a baseline, and the objective is to reconstruct a surface shape model of the whole asteroid. You're given a ground truth to compare your shape model with the truth, with a previously computed shape for this asteroid, which is what we're using to generate these images. And that's the challenge. Now, there's two parts to it. The first part is we've given you a template to start playing around with that to avoid troubleshooting and debugging, which is not fun. There is some running code, but the part that I invite you to explore, and I recommend maybe I'll stop talking for a while and I'll just walk around the room, is to explore how you could perform loop closure in your code. I can provide some hints here and there, but I encourage you to start from the code that you already see. Especially you will see add relative pose. And then if you look around, there's an add relative pose command. That's what I'm referring to. If you look around in the MATLAB documentation, starting from that add relative pose, there should be some hints on how to perform loop closure. Again, I'm here to help, and I can sketch out something on this laptop, but for now, let's try to pause there. Let's try to run the code. You should be seeing what's happening. And maybe in a few minutes from now, once you started thinking about it, I'll try to provide an overview of what the code looks like. But I think it might be more functional to just start playing around with the code for a few minutes, and then I'll provide an overview in a minute. Does that sound good with everyone? All right. And of course, before we formally move to the challenge, if you have any questions or as questions come up, feel free to.
More person instead. Yes. Good question. Yes, too. Yeah, it's well, right here, but yeah, yeah. Yeah, it's a lot. But when it's trees, nice, yes, yeah. Better on it's surface, it's one place. And it finds here, see this line, see the more water. And I hear all the other things.